In this video, we will be looking at a couple of sinusoidal applications. And we're going to start with a somewhat familiar one, which is a pendulum. So a pendulum has a length of 25 centimeters. It is displaced 5 centimeters from its equilibrium position and then released. So just thinking about the scenario here, let's say this is the central line. You have a pendulum that is 25 centimeters. It's displaced 5 centimeters. Didn't specify to the right or left. Here it is. It's let go and it just rocks back and forth 5 centimeters on each side. And the length of the pendulum is 25 centimeters. All right, so there's the scenario. The period of a pendulum is given by the formula T equals 2 pi times the square root of L over G, where T is the period in seconds, L is the length of the pendulum in meters, and G is the acceleration due to gravity, which is 9.8 meters per second squared. And we're going to calculate the period of the pendulum to 1 decimal place. Now, the period is just the length of time it takes for the pendulum to come back to its original position. So do 1 cycle, so 1 back and forth. So our period T is going to equal 2 pi times the square root of the length in meters, so not 25.25, divided by acceleration due to gravity, which is 9.8. Now, if you punch this into your calculator, you're going to get approximately 1.0 or just 1 second. So that's nice. Now we can find a function to represent the horizontal position of the pendulum as a function of time. So I'm just going to introduce some variables here. I'm just going to say, I'm talking about horizontal position, so let H represent horizontal position in centimeters, and this is with reference to time, so let T represent time, and it will be in seconds. So H of T is going to equal, so what's happening with this pendulum? It's pulled, and it starts 5 centimeters away from equilibrium. So I'm just going to take this diagram that I have at the top and kind of draw it in terms of time and horizontal distance. So it starts 5 centimeters away. It's let go, and what does it do? It comes to the center, goes 5 centimeters in the other direction, then comes back. And that takes 1 full second. Then it goes back and forth again. Now another second has passed. So here's our scenario. And if you look at this, your central axis is 0, so there's nothing going to be added at the end. The amplitude of this function is 5, so I'm going to start with that. My function is starting at a maximum, so it must be a positive cos. And the period is 1, which means my k value will be 2 pi over 1, which is just 2 pi. So 2 pi times t. There's my function. Now this is great because now we can answer some follow-up questions. The first one being, determine a function to model the horizontal velocity of the pendulum bob as a function of time. So that's our first derivative. So because I'm doing velocity, I'm just going to say, yes, I'm taking the derivative of that horizontal distance function, but I'm also going to relabel it as velocity. Okay, so to take the derivative of this, we have a chain rule. So cos is the outside function, 2 pi over 2 is the inside function. The derivative of cos is negative sine. I'm actually just going to put a negative in front of the 5 and then do the sine. Copy paste your inside function. Now it's time for the derivative of the inside, which is just 2 pi. I'm just going to clean this up. Just multiply the negative 5 with the 2 pi. So negative 10 pi and then times sine of 2 pi t. And now determine a function, to model the horizontal acceleration of the pendulum bob as a function of time. Okay, which means we need the second derivative. So the second derivative of that original equation will be acceleration. So now, again, we have a chain rule here. Sine is now my outside function. 2 pi over t is my inside. The negative 10 pi isn't affecting much. So the derivative of sine is cos. Copy paste the inside. Now let's take a derivative of the inside, which was 2 pi. And again, just to clean up, I'll multiply the negative 10 pi and the 2 pi so that we have negative 20 pi squared and then cos of 2 pi t. So we have acceleration, we have velocity, and we have the original function. Now notice that with all of these functions, they're pretty generic sine and cos functions. The numbers out front, the 5, the negative 10 pi, the negative 20 pi squared, they represent that a value, and the absolute value of a is the amplitude. They all have a central axis on the x-axis, so that amplitude also represents the max and min values. So the max and min of my original 5 and negative 5, of my second one 10 pi and negative 10 pi, of my third one 20 pi squared and negative 20 pi squared are the max and mins of the position, of the velocity, of the acceleration. So I actually know all my max and min values just because this is quite a generic sinusoidal function, like the format of it. So that's nice to note. Anyway, let's go on to what the next question is actually about, which is determine the maximum speed of the pendulum and when it occurs. Now we do have some options here. We're trying to find the maximum speed, so I'm going to use my velocity equation here. Just going to write it down. I have two options. Anytime I think of max to min, I think of, oh, let me take a derivative. So I can take the derivative, which we already have actually, it's the acceleration. Set it equal to 0, solve for time, and then plug in your time into velocity and see what those maximums are. And that's great and everything, but I could also, just looking at this function, this is a pretty generic sign, like I said already, which means if I were to graph this function, it's a sine function. So that starts at the origin. It's reflected. So I'm expecting something like this for my function. And my max and mins, I already know are 10 pi because of this a value out front. So I actually already know the maximum speed. It's 10 pi, what were the units? Centimeters per second. I know some of, like, I also have negative 10 pi, but remember in terms of velocity, that negative tells us about the direction. So I actually already know the max speed. It's 10 pi centimeters per second. So if I already know the speed, the only other part of the question I have to focus on is when does that speed occur, which means I'm just going to set velocity equal to 10 pi. So I don't even actually have to use one of my derivatives. I mean, I am using the first derivative, but I don't need to use my acceleration. Now, again, I could have, if I didn't recognize this velocity function as a generic sinusoidal function and I couldn't see the maximum there, I could use the derivative of velocity, set it equal to 0, and solve for those optimal values. But since we do have this connection, I'm just going to set velocity equal to 10 pi and solve. So I'm going to divide by negative 10 pi. Now actually, I did write 10 pi in here, but the max and mins occur at 10 pi and negative 10 pi. So I'm actually going to use both. And when I divide positive 10 pi by negative 10 pi, I get negative 1. But when I divide negative by negative, I get positive. So I have plus or minus 1 equals sine of 2 pi t. And now I think, okay, when is sine equal to positive or negative 1 in that generic base function? Well, it's at pi over 2 and at 3 pi over 2. So that's what 2 pi t is equal to. Pi over 2 and 3 pi over 2. And now I'm just going to divide both sides by 2 pi, or multiply both sides by 1 over 2 pi. And when you see it like that, you kind of see, oh, the pi's cancel, and then we just have time equals a quarter. And then for the other one, same idea. When I multiply by 1 over 2 pi, I end up with 3/4. And I can use the period of this speed function to find the next points as well. The k value is 2 pi, so the period is still just 1. If I wanted more, I would just keep adding 1. So 5 pi, oops, not pi, 5 over 4, 7 over 4. Those are all answers. So now I can give a generalized expression for all the times. A quarter, 3/4, 5/4, 7/4. It looks like I'm just adding 2 over 4 or half a second to that original time. So therefore, the max speed of 10 pi centimeters per second occurs at t equals a quarter plus half a second, where the seconds is an element of all integers. And there we are. So this was one of those typical periodic function examples, like the pendulum. But we also have scenarios that when we draw a diagram, it creates triangles and we're forced to use some SOHCAHTOA. So that's the next example that we're going to look at. A piece of pipe is being carried down a hallway that is 10 feet wide. At the end of the hallway, there is a right-angled turn and the hallway narrows down to 8 feet wide. What is the longest pipe that can be carried, always keeping it horizontal, around the turn in the hallway? So let's draw this. We have a hallway. The first part is a little wider, then you take the turn, it's a little more narrow. So this one here is 10 feet, and this side here is 8 feet. And we're gonna have this pipe that's coming in, and at first, you know, as it goes down the first hallway, it's nice and horizontal or parallel to the hallway, but when we take the turn, we're gonna have to take this pipe and turn it a little bit so that it fits to then go down the next hallway. Now, if I want to make this pipe as large as possible, I'm gonna use this corner here. And my pipe will do something like this. That's the longest piece, because if I take a piece here, that's obviously smaller. This is smaller. So I want it to be as close to the corner as possible, okay? Now, this is great and everything, but I need to get some variables in here. Maybe you try to get some triangles in here, and I will do that right here. Here's the 10 feet, and I've created a right angle. Here's the 8 feet, here's a right angle, okay? And now maybe I can say, okay, this is the pipe from one corner to the other, but maybe I can just break it down, the hypotenuse of one of the right triangles and the hypotenuse of the other right triangle. And together they're gonna form the length of that pipe. Now, that's nice and everything, but this is definitely not enough. Anytime we did optimization questions, we needed a little bit more in here so that we can write our equation all about one variable. Because as we have it right now, let's do some let statements first. We have x representing the x rep part of the pipe. our diagram is showing that, so let y represent other part of pipe, and let L represent total length. So as of right now, what we have is length equals x plus y. I can't take the derivative of this to optimize it, okay? But what I can do is add a little angle in here. Now the angle that we have there is going to be the exact same as the angle down here, because it's the same line, it's going in at the same angle, and it's hitting the triangle at a horizontal angle, so they have to match. Now why this is helpful is because now I have a reference angle, I have a known side, and then I have another one with a variable. I can do a little SOHCAHTOA here. So in this triangle, 10 is opposite, x is hypotenuse. I'm thinking sine theta equals opposite, so 10 over hypotenuse x. If I cross multiply, x goes with sine theta, 10 times 1 is 10, then I can divide both sides by sine theta. Fantastic, that can go in for x. Gonna do the same thing for the other triangle, but this time 8 is adjacent, y is hypotenuse, so seems like cos theta is the way to go here, and it's equal to 8 over y, and when I cross multiply, I'll end up with 8 over cos theta. That can also go in place. So now I have expressions for x and y all in terms of that angle theta. So length in terms of theta equals 10 over sine theta plus 8 over cos theta. And I'm just going to make a little note here. Let theta represent angle between pipe and wall. Now, a restriction we have to add in here. I have a function for the length in terms of theta, so I need a restriction on theta. And just looking at the diagram, just thinking about it logically, theta is going to have to be between 0, okay? And if theta is 0, that means our pipe is just right here, perfectly horizontal. Or the highest it can be is 90 degrees or pi over 2. And if that angle was 90 degrees, then it's touching the other wall. Now, just a note here, if theta is actually very close to 0, or if theta is 0, the pipe won't make the turn. And if it was 0, then in reality, this pipe can go on forever. Or if it was touching the other wall, it would go on forever. But again, these aren't logical values. Like, we're gonna get very high numbers here, but the pipe won't make the turn. So there has to be a happy spot somewhere between 0 and pi over 2. And I'll talk about that more when we get to the testing values portion of this. But right now we have a very nice function here for the length. We need to find that largest pipe. So let's take a derivative and set it equal to 0, like we did back in optimization. Now here I have a bit of a quotient rule. So the derivative of 10 is 0. Subtract the derivative of sine is cos theta, and that'll get multiplied by the original top, all over sine squared theta, plus the derivative of 8 is 0, and then I'd be copy pasting cos theta, which I forgot to show that here. The derivative of 10 was 0 times sine theta. And then subtract. The derivative of cos theta is negative sine theta, so I'm just going to turn that negative into positive, times 8, all over cos squared theta. Now just a little bit of cleanup here. I have negative 10 cos theta over sine squared theta plus 8 sine theta over cos squared theta. And now it's cleaned up. I'm going to set my derivative equal to 0, and I'm going to solve. Now, I can either get myself a common denominator, or I see two fractions, I can bring one over and cross multiply. Choice is yours. I think I'm going to bring the fraction over. And when I cross multiply, the 8 sine theta will multiply with sine squared theta, so 8 sine cubed theta, and the 10 cos theta with cos squared theta, which is 10 cos cubed theta. Now, whenever we've solved trig equations in the past, we tried to make everything in terms of one function. Sometimes we were able to factor, sometimes use trig identities, but whenever we ended up with something like sine equals cos, in order for us to make this all in terms of one function, dividing both sides by cos, or in this case cos cubed theta, would be helpful, because on the right side the cos cubed thetas cancel out, and on the left we end up with tan cubed theta. Okay, now when I do divide out that cos cubed theta, we do have to think in the back of our heads, oh, there is a little bit of restriction here. Cos theta is equal to 0 at pi over 2 or 3 pi over 2. So my answers definitely can't be those values. Now, it obviously can't be 3 pi over 2 because that's not even in our restriction, but definitely can't be pi over 2 because then I would have an error, okay, or an undefined value. Okay, from here, I'm going to divide both sides by 8. Okay, and then we can take the cube root of both sides to see what tan theta is equal to. Okay, and actually, I'll just keep it like that, and then, or not 10 over 8, I'll keep it as 5 over 4, or 1.25, and when I find my theta, I'll just keep the cube root instead of losing accuracy right away. Now, typically with tan, and thinking of the cast rule, tan is positive in quadrant 1 and quadrant 3, but because our restriction is that theta has to be between 0 and pi over 2, I only care about the quadrant 1 answer. So I don't really have to solve for alpha and do my full-on solving, just because taking a tan inverse will give me theta right away. Alpha and theta will be the same thing. So in our calculators, we're going to type in tan inverse of the cube root of 1.25, and I get 0.82. Okay, don't care about quadrant 3, it's outside of the domain. And now it's time to test. Okay, and we're going to be testing in that nice length formula that we had, so this one here, and we're going to test based on our restrictions and the critical point that we just got. Now, my restriction was from 0 to pi over 2. I'm not going to type in 0 because sine 0 is 0, so that's going to give me an undefined answer, 10 over 0. So I'm just going to test something close, like 0.1. I'm going to test my 0.82. And again, with pi over 2, not going to do it because, number one, it was a restriction from there, but also cos of pi over 2 is 0. So pi over 2 is 1.57 or something like that. So I'm just going to test 1.5. It's close-ish. And then I'll just go to my calculator and do 10 over sine 0.1 plus 8 over cos 0.1. And I end up with quite a large number, 108.21. Okay, gonna test 0.8, 10 over sine of 0.82 plus 8 of cos of 0.82, and for this one, I actually get something smaller. And then for 1.5, 10 over sine of 1.5 plus 8 of cos of 1.5, and again, I get a large number. I get 123.12. So looking at this, you might say, oh, I'm trying to maximize. Maybe 1.5 is the best way. But thinking back to what I said, as my pipe gets closer to either wall, so like getting very close to 0 or very close to that pi over 2, that pipe can be infinitely large, but that doesn't make sense here because if that angle is super close to 0, it's probably not making that turn anymore. So even though we're trying to find the longest pipe possible, when we're testing, it's actually going to be the smaller dimension here, because the other ones, as theta approaches 0 or as theta approaches pi over 2, the length approaches infinity. And obviously that doesn't make sense. So our winner is right here. So therefore, the max length of the pipe that can fit through that corner is 25.40 feet. And there we have it. So this is just one style of question where our diagram creates this right triangles. We're able to use SOHCAHTOA and then go from there with a quotient rule and then a little bit of trig solving at the end.